We're going to push through. We're going to get all this done today. You guys are going to, we're doing it. We're not taking any prisoners. We're not playing any games. No, I'm just kidding. We're busting through it though. We've got like 4 more sections. All right, so this next section, approaches for coping with the load. Approaches for coping with the load. Oh, that guy's cool. He's actually running in the water. Maybe he's just washing his hands. I can't tell. I think he got in. Okay, anyway. Now that we have discussed the parameters for describing load and metrics for measuring performance, we can start discussing scalability. Scalability in earnest. How do we maintain good performance even when our load parameters increase by some amount? An architecture that is appropriate for one level of load is unlikely to cope with 10 times that load. If you are working on a fast-growing service, it is therefore likely that you will need to rethink your architecture on every order of magnitude load increase, or perhaps even more often than that. People often talk of a dichotomy between scaling up, vertical scaling, moving to a more powerful machine, and scaling out, horizontal scaling. Oh, we're dying. Distributing the load across multiple smaller machines. Distributing load across multiple machines is also known as shared nothing architecture. A system that can run on a single machine is often simpler, but high-end machines can become very expensive. So, very intensive workloads often can avoid scaling out. In reality, good architectures usually involve a pragmatic mixture of approaches. For example, using several fairly powerful machines can still be simpler and cheaper than a large number of small virtual machines. While distributing stateless services across multiple machines is fairly straightforward, taking stateful data systems from a single node to a distributed setup can introduce a lot of additional complexity. For this reason, common wisdom until recently was to keep your database on a single node, scale up, until scaling costs or high availability requirements force you to make it distributed. As the tools and abstractions for distributed systems get better, this common wisdom may change, at least for some kinds of applications. It's conceivable that distributed data systems will become the default in the future, even for use cases that don't handle large volumes of data or traffic. Over the course of the rest of this book, we will cover many kinds of distributed data systems and discuss how they fare, not just in terms of scalability, but also ease of use and maintainability. The architecture of the systems that operate at large scale is usually highly specific to the application. There is no such thing as a generic one-size-fits-all scalable architecture, informally known as magic scaling sauce. The problem may be the volume of reads, the volume of writes, the volume of data to store, the complexity of the data, the response time requirements, the access patterns, or usually some mixture of all these plus many more issues. For example, a system that is designed to handle 100,000 requests per second, each 1 kilobyte in size, looks very different from a system that is designed for 3 requests per minute, each 2 gigabyte in size, even though the two systems have the same data throughput. An architecture that scales well for a particular application is built around assumptions of which operations will be common and which will be rare, the load parameters. If those assumptions turn out to be wrong, the engineering effort for scaling is at best wasted. Oh no. And at worst, counterproductive. That sucks. In an early stage startup or an unproven product, it's usually more important to be able to iterate quickly on a product feature than it is to scale on some hypothetical future load. That's a good point. That's a good point. Even though they are specific to a particular application, scalable architectures are nevertheless usually built from general purpose building blocks arranged in familiar patterns. In this book, we discuss those building blocks and patterns. Okay. We did.